Welcome to this lecture on digital computer electronics. We are discussing combinational logic circuits, and we'll start with addition and subtraction circuits. Let us start with a simple circuit for addition. We have two bits A and B that are to be added to generate S for sum and C for carry. According to this truth table, we have four options for the two bits 0, 0, 0, 1, 1, 0 and 1, 1. So for 0, 0 the sum is 0 and carry is 0. For any of the bits A or B being 1, the sum will be 1 and the carry will be 0. It's only the one condition when both A and B are 1, 1. Then the sum will be 0 and the carry will be 1. If we want to express this sum as in terms of A and B, we'll express it that it is 1, sum is 1 when we have such type of condition A not B or AB not. These are the two central conditions for the sum. And if we see that what is this expression is simply an exclusive OR of A and B. So we can express the sum as A exclusive OR B. In the same way, we have the carry signal C, and if we express it in terms of A, B, then it is 1 only when both of the inputs are high or 1. So this will be A and B. So the carry will be given by AB. So if we now make a circuit for this, it will be a simple exclusive OR gate giving the sum and a 2-input AND gate giving the carry. In the same way, if we have another truth table for the subtraction of the two bits, B is to be subtracted from A, then we have for all the four conditions, there's only one condition where B cannot be subtracted from A, is that when A will be 0 and B will be 1. So for only that condition a borrow is to be generated. For all other conditions the difference will be given by D. So if we have to generate the another borrow signal, so that will be generated from A not B. So the difference is again the same which was in the sum circuit, addition circuit. Now in the difference we have the difference also given by the same expression. So the difference is A exclusive OR B, but the borrow W will be given by A not B. So if we make the circuit, it's again a simple exclusive OR circuit for the difference and AND gate for the borrow, but one NOT is used for meeting the condition that when A is 0 and B is 1, only at that point we have to generate the borrow signal. Now let's see the full adder circuit. The difference between the half adder circuit and full adder circuit is only that the carry of the previous sections is not taken at the input. So if we have a truth table of full adder, that has to include the carry in with inputs A and B. So there are now 3 inputs and 2 outputs. A, B, C in are the 3 inputs and S and C out are 2 outputs. So the outputs S and C are to be expressed in terms of the inputs. So if we see now, there are 8 different conditions for the inputs A, B and C in. Out of those 8 conditions, sum S is 1 for 4 conditions, and if we want to express that how sum can be expressed, we have to write the expression for these 4 conditions. For all other conditions the sum is 0. So for these 4 conditions we can write the expression for the sum. It will be given by S is equal to A naught B naught C in, or A naught B C in naught, or A B naught C in naught, or A B C in. If we take C in common from first and the last term, and C in bar or C in naught from second and the third term, then we'll have the expression like this. Now in this expression we have A naught B or A B naught, that is A exclusive or B, and we have again A B or A naught B naught, that is exclusive NOR of A and B. So if we again try to simplify this, this will be A exclusive or B with C in naught, and of these two, or we have exclusive NOR of A and B and ended with C in. So this is exclusive OR of one and not of the other term. Then it is exclusive OR of all the 3 terms. That is, this expression is further simplified to A exclusive OR B exclusive OR with Cn. So if we have now the sum expression as exclusive OR of the 3 input terms. In the same way, C out is also 1 at 4 instances. If we write these 4 instances in terms of the expressions, then C out will be equal to ABC in naught, or A naught BC in, or AB naught C in, or ABC in. Now if I again take C in common from the terms second and third, and AB common from the first and the last term, I will get a solution like this. So this expression can be further written as that it is exclusive OR of AB with C in, and then it is AB or A and B. So because C in plus C in naught is equal to 1, so this is only AB. Now the expression for the sum and the carry signals has been generated. So these expressions can help us to design the circuit, and if we design that circuit implementation will be like this. So two half adders joined together to generate S, and the carry of the two half adders are to get the C out signal. So this is the implementation of the full adder circuit. So again we have this full adder circuit. The full adder circuit is now can be written as the two half adders, and we can express this as a black box having three inputs A, B and C in, and two outputs C out and S. So a full adder circuit will be a black box written as FA, means full adder, having three input signals A, B and C in on the left, and S and C out as the outputs on the right hand side. We can combine such black boxes to have, this is a 1-bit addition, we can have the 2-bit addition, 3-bit addition, 4-bit addition, a circuit of 4 bits. A circuit for the addition of 4 bits, A0 to A3 are the 3 bits added to be added to B0 to B3, and you see that carry out of the first stage is given to the carry in of the second stage. So the final carry out will be at the last stage, and the input carry in is grounded because there is no previous section here. So this is a simple 4-bit binary adder circuit. Now let's move to the full subtractor circuit. Again we have a truth table of 3 inputs now. Borrow in is the additional bit or signal that is to be considered with A and B to get the difference D and the borrow out. So again this D and W out, two signals are to be expressed in terms of A, B and W in. So again we can see here that D is 1 at 4 instances. So these 4 instances can represent D. So the D will be given by A naught, B naught, W in, A naught, B, W in naught, or A, B naught, W in naught, or A, B, W in. So this is a sort of same expression, and if we go on solving on the same lines as was done in the full adder circuit, we get finally the difference is the exclusive OR of the 3 input signals. So there is no difference between the adder and the subtractor in terms of addition or difference signals. Both depend on the exclusive OR of the input signals. Now if we have to generate the borrow out, W out, then the borrow out will be again an expression of 4 conditions, 4 events. So these 4 events can be written like this, that W out is equal to A naught, B naught, W in, or A naught, B, W in naught, or A naught, B, W in, or A, B, W in. If we again try to simplify this, we again get the same type of expressions as were got in terms of the full adder. Now we have here the borrow out expressed in terms of the 3 input signals. If we now implement this circuit for the difference and the borrow out, it is simple integration of 2 half subtractors. In the same way as that in the adder circuit, 2 half subtractors are joined to generate the difference D, and the borrow out of the 2 half subtractors is joined by an OR gate to give the final borrow out. Again, show the black box of these 2 half subtractors and the join of their borrow outs through an OR gate to generate the final borrow out. So if this black box is again simplified, it is written as that this is a full subtractor black box having 3 inputs A, B and borrow in, and 2 outputs D the difference and W the borrow out. In the same way, if we have number of bits to be subtracted, we can have this 4-bit subtractor circuit in which B0 to B3 are the 4 bits representing the number which is to be subtracted from the number represented by 4 bits from A0 to A3. So again here the borrow out of the first section is connected to the borrow in of the next section. In the same way that 4 bits can be subtracted. Now we have a 4-bit binary adder cum subtractor circuit. So this is a circuit. Here, instead of giving directly the A0 to A3 bits, we are giving these inputs A0, A1, A2, A3 through exclusive OR gates. The next input of all these 4 exclusive OR gates is combined, and this is combined with the C in of the first full adder and written as O. So based on this O, we can have this 4-bit adder to work as adder and at other time as subtractor. If I use this O as 0, then all the bits from A0 to A3 will be passed simply through the exclusive OR gate and they will have no change. So in that way, the first carry in is also connected to 0. So there is no carry from the previous section, and so this condition is met that this is grounded. Now the 2 inputs from A0 to A3 one number and B0 to B3 another number can be added through this circuit to get the 4-bit output signal. But once this O is given as 1, the same circuit will perform subtraction. How will perform subtraction? The first thing that it will be 1, then the C in will be 1. Means a borrow has been given at the input, or we can say that 1 has been incremented in the first section, and then this 1 at all the inputs of the 4 exclusive OR gates will change A0 to A3, the 4 inputs, to their 1's complement. So the 1's complement is generated, and second thing is that 1 has been given an additional carry in the first section. So this sort of circuit will generate the 1's complement and also will add an extra bit at the first C in place. So what this will do, that this will generate 2's complement. When the 2's complement has been generated, then both of these inputs will get added to give the output subtraction result, and this method is based on what we call as the 2's complement method of subtraction. Let's end this lecture here. So thank you very much.